Okay, so what we're looking at then today is the binomial expansion. Binomial 2 expanding, when we've got two variables, two numbers, two letters in brackets, and we're trying to expand them to a certain power. And what we use in order to do this is Pascal's triangle, which we have had a look at. Pascal's triangle starts off with our 1 at the top, then 1 on either side. The first and last numbers are always 1. First and last numbers are always 1. And then the numbers in the middle are made by the sums of the two numbers above them. So here, the middle of 1 and 1, and I know that we know this, is going to be the sum of 1 plus 1, which obviously gives me 2. We keep going, 1 on the outside, 1 on the outside. Again, then I've got the sum of 1 and 2, which gives me 3. The sum of 3 and 1, which gives me 3, and so on and so forth. So we're going to keep bringing our triangle down for as long as we need it, which we'll talk about in a second. 1's on the outside, 1 plus 3 gives me 4, 3 plus 3 gives me 6, 3 plus 1 gives me 4, 1 on the outside, 1 plus 4 gives me 5, 4 plus 6 gives me 10, 6 plus 4 gives me 10, 4 plus 1 gives me 5, and 1 on the outside. Nice. And we can keep going for as long as we want. This triangle goes on forever and ever and ever. And it's useful because it tells us the coefficients of our expansions within these binomial expansions. So, how do we use it? Well, each row is an ascending power depending on how much we're expanding by. What I mean by this, if I'm expanding to the power of 0, the coefficient is 1. That makes sense, right? Anything to the power of 0 is 1. Then, if I'm expanding to the power of 1, the coefficients are 1 and 1. Again, which makes sense. If it was x plus 2 to the power of 1, that's just 1x plus 1 lot of 2. To the power of 2 is here. To the power of 3. To the power of 4. I don't know why my pen's being silly. And to the power of 5. So, in this question then, x plus 2 to the power of 5, we are going to be using this line of Pascal's triangle. 1, 5, 10, 10, 5, 1. And so then my first step, once I've decided which line of the triangle I'm going to use, is I'm going to write out those numbers, and I'm going to write them out one on top of each other. And I think this makes our working out much easier. So 1, 5, 10, 10, 5, 1. Okay, then I've got to fill in the rest. So, what this means is that our first number, our first letter variable number in our bracket, in this case x, goes in descending powers from 5. If it's the power of 4, it's descending powers of 4. If it's descending powers of 3, descending power of 3, and so on and so forth. What that means is, this is going to be 1 lot of x to the power of 5. This is going to be 5 lots of x to the power of 4. We've got 10 lots x to the power of 3. And I'm just filling it in, going down. I think writing it out this way, on top of each other, makes our lives much easier. X to the power of 2, x to the power of 1, x to the power of 0. Okay? Nice. That's our x's. Then I'm going to move on to the next part of our bracket, next part of our expansion, which is 2. And now, and you can take a guess, rather than going in descending powers, it's going in ascending powers from 0 up to 5. So, 2 to the power of 0 times 2 to the power of 1 times 2 to the power of 2 times 2 to the power of 3 times 2 to the power of 4 times 2 to the power of 5. Notice, right, that the sums of the powers are always 5. That's a nice way to check that you're doing it right. Some people like to, in fact, draw it going up from there. So they go 5, 4, 3, 2, 1, 0 the x's, and then 5, 4, 3, 2, 1, 0 going up. Whichever way you like to do it, as long as those powers always add up to 5. Okay, we're basically there. Then I just have to bring it together and simplify. Well, 1 times x to the power of 5 is just x to the power of 5. 2 to the power of 0, this 2 to the power of 0 here, anything to the power of 0 is just 1. So it's 1 times x to the power of 5 times 1. I can even write that above if that's helpful. 1 times x to the power of 5 times 1. In fact, rather than do that, I'm going to write it next to it so we're going to have, for posterity, really clear working out. right? This is going to be 1 times x to the power of 5 times 1, which gives me x to the power of 5. This is going to be 5 times x to the power of 4 times 2. Well, 5 times x to the power of 4 is obviously 5x to the power of 4 times 2 is going to be 10x to the power of 4. Okay, for the next one, 10 times x to the power of 3 times 2 squared. Well, 2 squared is 4, so I can just write 5 times x cubed, x to the power of 3, times 4. Well, 5 times x cubed is just 5x cubed, times by 4 gives me 20x cubed. So I'm bringing together all of these things into one term. Okay. Then I've got 10 times x squared times 2 cubed. Well, again, 2 cubed is just 8. So I can write 10 times x squared times, I don't know why my pen's being so strange, times 8. Well, 10x squared multiplied by 8 gives me 80x squared. Keep it moving. 5 times x to the power of 1 is just, well, 5x, isn't it? Well, I can write that 5x1. 2 to the power of 4. 2 times 2 times 2 times 2 gives me 16. Well, 5 times x1 is just, well, 5x, right? Times by 16 gives me 80x. I don't need that power of 1, do I, if it's just the power of 1? And finally, 1 times x to the power of 0 times 2 to the power of 5. Well, that's 1. X to the power of 0 is obviously just 1, right? Anything to the power of 0 is 1, including x, times 2 to the power of 5, which is 32, equals 32. There, I've expanded it all, and we just have to bring our nice terms together into our answer. So my final expansion of x plus 2 to the power of 5 is x to the power of 5 plus 10x to the power of 4 plus 20x to the power of 3 plus 80x to the power of 2 plus 80x plus 32. Nice. Okay, have a look, have a think. This does get ever so slightly more, I'm not going to say complicated, but perhaps more convoluted, when instead of having an x, we might have 3x or 4x or 5x, right? A value, a coefficient, along with our x. And so I'm going to have a look at that as we move on now. Oh, no, I'm not. Press the pen. There we go. Let's move on now. So now, if I have this, expand. I don't know why my pen's being so strange. Expand. Let me zoom in maybe. 3x minus, yeah, we can make it difficult. 3x minus 4 to the power of 4. Okay, zoom back out. It starts with exactly the same thing again, right? We need to know what line of our triangle we're going to use. So again, we're going to start off by writing out the triangle. Let's start off. We know 1 starts at the top. Then 1, 1 underneath. 1, 1 on the outside. 1 plus 1 in the middle gives us 2. 1 on the outside. 1 plus 2 gives us 3. 2 plus 1 gives us 3. Then I've got 1, 4, 6, 4, 1. I can even keep it going if I need to. 1, 1 on the outside, and then 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 gives me 10. 4 plus 1 gives me 5. Okay, and which one are we going to use? Well, this first line, what people sometimes forget or get wrong is they put 1 on that first line. No, right? That first line, that just 1 is to the power of 0, which obviously we're never going to use, but it's there. The second line is to the power of 1. The third line to the power of 2. To the power of 3. To the power of 4. To the power of 5. So in this question, 3x take 4 all to the power of 4, we're going to be using that fourth line. 1, 4, 6, 4, 1. So I'm going to sort of highlight that, show the examiner I know exactly what I'm talking about, and write out those numbers, again, in a pile, or not in a pile, one on top of each other. So I've got 1, 4, 6, 4, 1. Give myself not lots of space to do whatever working out I need to do. Okay, then I'm going to do the same thing. So before it was x. So it was descending powers of x, right? x5, x4, x3, x2, x1. Now we've got 3x. What we've got to do is be careful. What some people do is they put, well, 3x to the power of 4. No, right? What this means is 3x, why is my pen being silly? 3x all to the power of 4. All to the power of 4. And that is different. I'm going to talk about in a second. The next one. I've got my hand on the iPad. Let me try that now. The next one. I've got to have my hand on the iPad. 3x, oh, it is because of that. All to the power of 3. The next one. 3x to the power of 2. And so it's descending powers now of the 3x. 3x to the power of 1. 3x to the power of 0. Now it's the same thing with our negative 4. Remember, that's a minus 4, a negative 4, because there's that minus in the bracket, so we'll go green. So then it's going to be ascending, going up powers of negative 4. So we're going to have negative 4. Notice I'm putting it in brackets to make sure that I'm not making any mistakes here. Negative 4 to the power of 1, negative 4 to the power of 2, negative 4 to the power of 3, negative 4 to the power of 4. Beautiful, beautiful, beautiful. In fact, now I'm going to move this page over so I can really, oh, there we go. So I can really clearly see now this next stage of the working out. And there will be stages, right? I know the temptation to sort of rush straight into an answer here. There's no need for that. Much better to guarantee ourselves 3, 4, 5 marks here than make silly mistakes, which is so easy to do when we're dealing with these high powers. So 1 is just 1. I can write 1. Now, 3x to the power of 4 is not 3x4. I see people write this. No. Why not? Because we are not doing 3 times x to the power of 4. We are doing 3x to the power of 4. 3x times 3x times 3x times 3x. So we're going to do 3 to the power of 4 and x to the power of 4. So 3 times 3 times 3 times 3 gives me 81 x to the power of 4. Multiplied by negative 4 to the power of 0, or anything to the power of 0 we know, we're confident, is just 1. Fine. Okay, let's bring it together now. Well, 1 times 81x 4 times 1 is just 81x to the power of 4. Fine, my handwriting's got worse because my iPad pen's being silly unless I'm holding it in a weird way. Okay, next one. 4 times 3x cubed. Well, 4 times 3x to the power of 3. Again, it's not 3x cubed, it's 3 cubed and x cubed. So we're going to do 27x cubed multiplied by negative 4 to the power of 1, which is just negative 4. Okay, well, 4 times 27, I'm going to get one of these wrong, but 4 times 27 gives us 108. Now, 108 times negative 4 is going to be negative 432x cubed. Yeah? Nice. Next one. We're going to do 6 multiplied by 3x squared. Well, 3x squared is 9x squared when we expand it, because 3 squared is 9, multiplied by negative 4 squared. Well, negative 4 squared is positive 16. Negative times a negative gives you a positive. Okay, well, 6 times 9 is going to give me 54x squared, and 54 times 16. Lots of ways of doing it. You could do column method, or you could just do 50 times 16 is 800. 4 times 16 is 64, so it's going to be 864x squared. Remembering that it's positive because that negative 4 squared came out as a positive 16. Okay, next one. 4 multiplied by 3x to the power of 1, so that's just 3x, multiplied by negative 4 cubed. Negative 4 times negative 4 is 16. 16 times negative 4 is negative 64 again. Okay, so 4 times 3x gives you 12x. 12x times negative 64. Well, 60 times 10, 64 times 10 is 640. 64 times 2 is 128. So 640 plus 128 is 768. I think I've done that right. So then it's going to be negative 768x. It's going to be embarrassing. I've got these wrong. 4 times 3 is 12. Yeah, 640 plus 128. Yeah, that's right. And then finally, my last one. 1 times 3x to the power of 0. Anything to the power of 0 is just 1. Multiplied by negative 4 to the power of 4. Okay, well, negative 4 times negative 4 is 16. Times negative 4 is negative 64. Times 4 again is positive 256. So it's just 256. Again, there's no value of x here because 3x to the power of 0 is just 1. And we've done it. And we just bring all of our answers together in one beautiful 3 or 4 mark expansion. So my answer is 81x to the power of 4. Take away, because of my minus there, don't forget, 432x cubed. Plus, because it's a positive now, 864x squared. Take away 768x. Add 256. And we have a perfect binomial expansion of the bracket 3x minus 4 to the power of 4.